Hi, my name is Aarifah Haleem, and today I will be discussing my MEng project presentation, Vehicular Aerodynamics Wind Tunnel Testing of Unmanned Aerial Multirotor Vehicles and Wall Interference Corrections. Unmanned aerial multirotor vehicles are more commonly known as multicopters or drones. Their vertical takeoff and landing or VTOL capabilities and their ability to hover, maneuver, and carry payload make them increasingly popular. They are commonly used in reconnaissance applications such as surveillance, land surveys, and recreational aerial imagery. Therefore, the modeling of the aerodynamics and flight characteristics of these vehicles is highly desirable. The goals of this project were, first, to study the aerodynamic characteristics of the unmanned aerial multirotor vehicle, the body itself, including its additional components and not considering the rotors. Second, to study the effects of test section walls on the model and to set up a method to apply wall corrections to the test data. And finally, this project is intended to support a separate ongoing study on aerodynamic modeling of maneuvering multirotor vehicles. This project was conducted using the Large Subsonic Wind Tunnel at Ryerson University. It is a subsonic, closed-circuit, closed test section wind tunnel that is 13 meters long and 5 meters wide, represented by the diagram on the right-hand side. It is composed of the settling chamber with screens, where the entering airflow is straightened and stabilized. This is followed by the contraction cone, which is a section of reducing area where the flow velocity is increased to the desired testing level. The air then enters the constant area test section, where the model can be mounted and tested. From here, the air enters the diffuser, a section of increasing area which decelerates the air and increases the pressure. However, rather than discharging the air into the atmosphere, it returns to the settling chamber through a series of 90-degree turns, using turning vanes to reduce pressure losses. The air flow through the tunnel is controlled by the fan. The test section of the wind tunnel used is a rectangular closed test section. It allows for the installation of an external load balance on the roof of the test section as well as mounting supports for the model. The use of a closed test section with a flat floor also allows for models to rest on the surface if required. Closed test sections pose a few challenges, including constraining the airflow. This produces additional effects on the flow field, which may skew the test results of the model. The test section of the wind tunnel used, shown in the figure, is 2.75 meters long and has a cross-section of 0.914 meters by 0.914 meters. The corners of the test section walls also have 45-degree fillets to control boundary layer growth and flow separation. The test section also has a glass window to view the model when testing. The model chosen as the unmanned aerial multirotor vehicle was the DJI Matrice 210 RTK, which is a quadrotor drone used for aerial imagery. Testing was carried out to reflect the vehicular aerodynamics requirement alone, not including the rotors. That is, flow only over the body components was considered. The image on the left shows the full assembly of the model consisting of 3D printed parts and wooden components. As labeled in the figure, the model components included the main body, the main battery, 2 landing gear, 4 arms, the RTK GPS antennae, the camera, the backup battery, the computer on the side, and a backup antenna. These components were tested in 9 configurations, shown in the table on the right, at 10 meters per second and 15 meters per second each, for a sweep of angles from minus 135 degrees to plus 135 degrees in pitch, roll, and yaw orientations. Configurations 1 to 6 were variant combinations of the components, whereas configurations 7 and 9 were repeat tests. The testing of the configurations was divided into a number of wind tunnel runs, where each run represented a different velocity, orientation, and sweep of angles. On the left, we can see an example of the model in the test section represented by configuration 1. The model was mounted on the end of the T-support, as we can see from the T-support attachment, and the T-support was fixed between the model support struts as described in the figure. The support struts, which connect to the external load balance installed on top of the test section, sense the lift, drag, and pitching moment. The angle of attack of the model was changed manually by increments of approximately 5 degrees. The true angle values, however, were recorded by 3 IMUs mounted within the model body aligned with the body axes. The table on the right shows the model orientations for pitch, roll, and yaw. As we can see, the pitch orientation of the model is achieved by mounting the model so that the front view is facing the free stream flow in the wind tunnel. That is, the longitudinal axis of the model and the free stream direction are parallel. Of course, the change in angle of attack for the model in this orientation represents change in pitch. Rotating the model counterclockwise by 90 degrees represents roll, and rotating the model clockwise from the pitch condition represents yaw. Prior to testing, calibration of the load sensors, pressure transducer, and temperature sensor were carried out to ensure accurate and stable readings. The tear values of the sensors, or their initial increment if any, were recorded prior to each run so that they could be eliminated from the test data. A base drag survey was also conducted for an empty test section, struts alone, and the struts with the T-support from 200 RPM to 1000 RPM in increments of 100 RPM. The test data would also be corrected for this base drag so as to obtain the data for the test model itself. Wind tunnels are used to simulate the real flow environment of a model so that the flow characteristics can be studied and modeled. Though there are advantages to having a closed test section, the walls are an introduced factor to the simulation which produce additional effects on the airflow. Examples include effects due to streamline curvature, downwash, buoyancy, and blockage. The effect of the test section walls on streamline curvature is to constrain the naturally curving streamlines occurring over a model in airflow. As a result, the flow accelerates and experiences a higher velocity. Downwash occurs when the higher pressure airflow below the surface of a wing tends to curl over the tips of the wing, forming wingtip vortices, and essentially dragging the upper airflow downwards off the trailing edge of the wing. A downward flow and velocity component is produced, which causes an increase in the angle of attack by an increment of effective angle of attack. The increased velocity also causes an increase in lift and induced drag. In a wind tunnel, the downwash component impacts the walls and causes very large increments in lift force. This also results in much larger angles of attack, leading to stall. Streamline curvature and downwash effects occur due to the characteristics of lifting bodies. Since the quadcopter being tested is a bluff body, only buoyancy and blockage effects are considered, which I will discuss in the next slides. Buoyancy in the wind tunnel is a result of the viscous air interacting with the walls of an empty test section. That is, it is not influenced by the presence of a model in the test section, but it can have effects on the forces felt by the body. Consider the figure shown on the slide. Since air is viscous, it has a no-slip condition against the wall at point A as it flows through the test section where the velocity of the air is 0. The velocity increases forming a velocity gradient until the velocity is equal to the free stream velocity at point B. This region of varying velocity is called the boundary layer. Because of the velocity profile of the boundary layer and the conservation of mass, the loss of velocity results in a loss of mass flow along the wall. This is known as a mass flow deficit and is represented by displacement thickness delta star. The effective displacement thickness on the cross-sectional area of the test section is shown in the figure on the right, where the original width and height of the test section are reduced by delta star. Because of the viscous nature of air, as the air flows along the surface, the displacement thickness tends to increase. This effectively reduces the cross-sectional area along the length of the test section in the downstream direction. From the continuity equation, we know that the reduction of area will result in an increase in velocity. Subsequently, from Bernoulli's equation, an increase in velocity results in a decrease in static pressure. This causes a horizontal pressure gradient in the test section from the entrance to the exit. Since force is a product of pressure and area, an increase in either of these causes the increase in force, which in this case is a horizontal drag force called buoyancy drag. The effect of buoyancy drag is to drag or pull the model downstream. Up to date, there is no method to prevent buoyancy. However, it is controlled by maintaining a nearly constant static pressure throughout the test section. Current methods include diverging the walls of the test section by half a degree to accommodate the thickening boundary layer, by introducing 45-degree fillets in the corners of the test section to prevent the growth of the boundary layer and flow separation, by having open test sections where the flow would not be constrained by the walls and have no viscous interaction, or slotted test sections where the boundary layer would not be allowed to grow. Also, by surveying the local static pressures in the test section and eliminating the induced pressure gradient from the test results. Wind tunnels are generally designed to have a minimal buoyancy effect by using the first three methods. Overall, however, the last method is the most commonly accepted method of accounting for buoyancy effects in the test section. Buoyancy corrections applied to the testing results showed the growth of the displacement thickness in the test section to stabilize after 0.5 meters length into the test section. The displacement thickness reaches a thickness of 3 millimeters by the end of the test section at 2.75 meters. The corresponding change in cross-section area was also shown to reduce up to the test section length of 0.5 meters, where it then became constant. By the end of the test section, the cross-sectional area available to the airflow reduced from 0.8345 meters squared to 0.8245 meters squared, or it reduced by 0.01 meters squared. Here, we can see the results of the buoyancy correction calculations where the drag coefficient due to buoyancy is found on the y-axis and the distance along the test section is found on the x-axis. Apart from a sharp increase in CD due to the growth of the boundary layer, very little variation of the drag coefficient is seen along each line, which represents each test run. For example, in the region of the model from 1.28 meters to 1.43 meters, the buoyancy drag coefficient varied by less than 1.9 times 10 to the minus 6 along the topmost run and even less towards the end of the test section. This implies that there was minimal static pressure gradient in the test section. Due to this, buoyancy corrections can be neglected from the results. The second type of wall interference effects that we consider are blockage effects. Blockage effects are a direct result of the presence of a physical body in the flow field of the test section. The model in the test section obstructs the airflow and effectively reduces the cross-sectional area of the test section. By comparing configuration 1, represented by the main body, and configuration 9, which is the full assembly, we can see that the presence of a body as well as the size of the body will surely have an effect on the airflow. Referring again to the continuity equation, the reduction of area leads to the increase of velocity and dynamic pressure downstream of the model. The total blockage effect consists of two components: solid blockage, which is the effect produced by the solid body in the flow. It is a function of volume of the model and the area of the test section. The second is wake blockage. This is the effect of the airflow accelerating as it leaves the wake, which is formed by the departing boundary layer of the model as it leaves the body. It is a function of the cross-sectional area of the model, or the model frontal area to the airflow, and the uncorrected drag coefficient. The total blockage effect is obtained by adding solid blockage and wake blockage corrections. Using this, the dynamic pressure is also corrected, which is used to non-dimensionalize the uncorrected drag coefficient. Due to discrepancies in test results for configurations 7 and 6, they were not included in the final results. Also, configuration 8 was conducted as a test run of the full assembly and tested at only 10 meters per second, so it too was not included in the final results. Blockage corrections were therefore applied to configurations 1, 3, 4, 5, and 9. Since this project was intended to support a larger separate study, the wind tunnel test results are still being processed. Therefore, blockage corrections were only applied to the available data, which were the pitch orientation runs. And here are the final blockage correction results. The corrections were applied to an angle of attack range of -10 degrees to +10 degrees. This is because, as discussed earlier, wake blockage is affected by the frontal area of the model. The effective model area faced by the airflow changes for greater ranges of angle of attack, and the percent error in corrected dynamic pressure was found to be very large. The graph on the right shows the percent error in corrected dynamic pressure for each accepted configuration with a value for the 10 meters per second and 15 meters per second runs. By applying the blockage corrections, configurations with larger frontal area and model volume experienced a greater percent error in corrected dynamic pressure, such as configurations 3 and 9. Configuration 9, which represents the full assembly, shows that applying blockage corrections prevents an error of 1.78% for 10 meters per second and 1.82% for 15 meters per second. Similarly, configuration 1 shows the percent difference of 0.55% and 0.56% respectively. The variation in dynamic pressure correction between velocities for each configuration is very small, only up to 0.04% as we see in configuration 9. The least difference is seen in configuration 5, which represents the body, battery, and legs. Both runs experience a dynamic pressure correction of approximately 1.20%, with a difference of 0.0015% between their two runs. The similarity can be attributed to the components and orientation of this configuration. The additional component of legs did not cause extra buffeting or obstruction at a higher velocity. This effect can be seen, however, by configurations 4 and 9, which had larger and more components. Overall, by comparing configuration 1 and 9, the application of blockage corrections achieves a 1.22% and 1.25% correction in dynamic pressure for 10 meters per second and 15 meters per second velocities respectively. Clearly, accounting for the blockage effect due to test section walls is necessary, especially when testing large models. In conclusion, The purpose of this project was to obtain results for the aerodynamic flow characteristics of the drone body and its components. Since the model was tested in a closed test section wind tunnel where the model was enclosed by walls, relevant wall interference effects were studied and applied accordingly. Blockage corrections were applied to available processed data, which were the pitch orientation runs. Additionally, the corrections were considered for runs where angle of attack ranged from -10 degrees to +10 degrees. A future scope from this study may be to understand the ranges of angles that should be considered when applying wake blockage corrections, which involves the model frontal area. Buoyancy effects were found to be negligible, so the buoyancy corrections were not included. The further application of this project would be to adapt the calculation method to include roll and yaw data, as well as to include frontal areas for different model orientations. This brings us to the end of my presentation. I hope you found it informative. Thanks for watching.